All right, so this week we are talking about climate change. So right off the bat, the first thing we're going to do is I'm going to give you a reminder that weather and climate are not the same thing. They're not the same thing. So we're not talking about changing weather, we're talking about changing climate. So weather is what's happening outside your window right now. Like right at this second, that's what weather is. Right? So this is short term. It applies to a limited area. It can change rapidly and it is difficult to predict. So we are not talking about weather. We are talking about climate. So climate is the average of many years of weather observation. So we're looking at something that's long term. It impacts a wide area. It changes seasonally, not daily or hourly, and it is measured over long spans of time. So it's not what's happening right now. It's on average what will happen this season. So climate is affected by a lot of things, right? So again, we're looking at that overall average of weather conditions is our climate. So it's going to be affected by a lot of the things. So first, abiotic, which are non-living factors. So these are things that are not alive that can impact climate, which are going to be things like latitude, so where you are on Earth, altitude, how high you are above sea level, ocean currents, if you're near a hot or a cool current, that's where like El Nino, seasonal rainstorms come in. Topography, right? So are you near water is one of the big ones. If you tend to be more water or near water, your climate's more stable than if you're in an arid or a dry location. Solar radiation, so how much sunlight do you get? Evaporation, so how much moisture is going to be in the atmosphere versus on like the land surface. Orbital variation, so just the way Earth orbits, and any volcanic activity, particularly when it releases ash into the atmosphere, which can have an impact, again, doubling back on that solar radiation. So biotic or living factors include transpiration, so we're talking water cycle, transpiration, respiration, photosynthesis, decomposition, and then even human digestion. So all those things that are going to impact the amount of gas in the atmosphere, the gaseous makeup of the atmosphere. So how much O2 versus CO2 versus water vapor versus methane, whatever else, those are all going to impact climate. So anything a living thing does to impact the atmosphere is going to impact climate. Anything a non-living abiotic could do might also impact climate. All right, so greenhouse gases. This is a phrase you've probably heard before, but I just want to touch on it so we are 100% clear on what greenhouse gases actually are. So greenhouse gases are gases that trap the sun's heat, and that's really important because hopefully you learned in 6th grade that warmth from the sun is the only thing that keeps us alive on our planet, right? So step one, the sun's radiation is going to travel through the Earth, right, or towards the Earth. About half is immediately going to get reflected or absorbed by clouds and the atmosphere. So atmospheric conditions absolutely are going to depend and impact how much sunlight gets reflected back, which leads us to step 3, which is where the rest of it reaches the Earth. So when it reaches the Earth, it's absorbed by oceans, it's absorbed by land. So we've got that radiant heat from the sun, that UV radiation. And then after it's reached the Earth, a couple things are going to happen. So some of it is going to get released back into space. So we're going to emit radiation just like we bring in radiation. Some of it is going to pass directly through the atmosphere, and most of it, so most of that heat we get from the sun is going to be captured and is going to be retained by those greenhouse gases. So we put a greenhouse around plants to keep that O2, CO2, photosynthesis respiration cycle stable. We use our greenhouse gases to kind of do the same thing. So it's going to adjust and affect the amount of heat we have on Earth, and that's going to help keep all our atmospheric cycles stable, and that's going to help keep all our weather cycles stable and our climate stable as well. So planets that don't have a lot of greenhouse effect are either very cold year round or they have huge temperature swings from day to night. And that just depends on its distance from the sun. So planets with very few greenhouse gases that are really far away, like Pluto, for instance, are going to be really cold. Planets that are closer to the sun, like Mars, that have very little greenhouse gases and very little atmosphere in general, are going to have an extreme temperature differential. So there's going to be about a 300-degree difference between high and low temperatures on Mars, and that's in a Martian day. So when it is the side facing the sun, is going to be extremely hot. The side facing away is going to be extremely cold because it's not currently receiving radiation and it doesn't have those greenhouse gases to kind of keep it warm throughout time. So planets that have a lot of greenhouse gases, like Venus has a ridiculously thick atmosphere that is primarily methane, which is a greenhouse gas. So the overwhelming majority of Venus's very large atmosphere is greenhouse gas, and that's going to make it very hot. So temperature on Venus is about 855 degrees Fahrenheit, which is bananas. And then there's Earth, which is just right. So at least for right now. So for right now, we're right where we need to be. So a small percentage of our atmosphere is greenhouse gas. The majority is going to be nitrogen, which is not considered a greenhouse gas. So we have this comfortable balance that keeps us warm, but not too warm, at least right now. So quite a few greenhouse gases do hang out in our atmosphere. So these 4 all occur naturally. You're always going to find them. They've always been there. So water vapor, carbon dioxide, methane, nitrous oxide, which is NO2. So all 4 of those are going to be those gases that keep heat trapped on Earth. So our greenhouse gas content of the atmosphere is being altered by human activity, right? If we flash back to the last slide where we've got carbon dioxide, that's a big one. So the fact that these greenhouse gases are being released to the atmosphere at a much higher than its natural rate is what's called climate change. So the fact that we are adding way more greenhouse gases to our atmosphere is going to change our climate because it's going to change our atmospheric conditions. When we have more greenhouse gases, on average, Earth is going to get warmer, but we're starting to see those more extreme switches that you see on other planets that have very different greenhouse gas levels. All right, so like I said, our carbon dioxide is the big one, right? So all of these graphs that I'm about to show you come from one of 2 places. They either come from NOAA, the National Oceanic and Atmospheric Association, or they come from NASA, the National Aeronautics and Space Administration. So those 2 groups are taking charge on climate change because they're the ones who largely control the satellites and the ocean buoys that collect data. So if you're the one who collects data, you kind of notice the data first and pay attention to it and help show other people that data first as well. So we've got an increase in carbon dioxide levels. So if we are looking from early 2000s, which I think this starts actually at 2000, goes from, it would start at 2004. If we go from 2004 to the present, that's in just 16 years, our parts per million of carbon dioxide has gone up really intensely. So that is a really steep line for carbon, like a really steep line for carbon. So there's no way to argue that we're not increasing carbon. There's just no way to argue that there's not increased carbon dioxide, and there's not enough volcanic activity or natural occurring processes that are going to allow for carbon dioxide to rise at this rate without human action. Not to mention, almost anything that uses energy is going to have some level of carbon dioxide output. So it's what's called a carbon offset. So anytime you're using anything that requires energy, whether that's for cooking or driving around town or using your laptop or your phone, those are all going to have some sort of carbon impact somewhere along the way. We're going to look into that more specifically next week. So since carbon dioxide is a greenhouse gas, the more carbon dioxide levels rise, the more Earth's average temperature changes. So our evidence of climate change, because this is another topic kind of like evolution that has some controversy around it, right? So we're going to be talking about the strict science. So we have evidence of climate change from a lot of different sources, and we're going to take just a quick peek at each of these. So we've got sea level rise, ice sheet mass, so the mass of ice sheets, particularly up at the North Poles. Summer sea ice coverage, again, that's going to kind of link to sea ice mass or ice sheet mass. I'll talk more about that when we get to that slide. Ocean acidification and the change in global average temperature. So we can tell that climate is changing because we can measure Earth's average temperature. All right, so the first one is going to be sea level rise. So as global temperatures increase, glacial melting and the expansion of water as it warms are leading to higher seas. So this is sea height variation. So this is on average the amount of change we have in sea level from 1993 up to the present. And this is on a NASA website. You can actually go and play with the graph and it'll tell you average rate of change at each year. So on average, Earth's oceans are going up, our sea level is going up at about 3.3 millimeters per year, which does not sound like a lot. But when you look at the difference that just an inch or two of water could make for places that are considered to be below sea level, that's intense. We've also got more liquid water in the ocean, which is one of the reasons we're starting to see more intense hurricanes and more intense weather events involving water and involving our oceans. Next up, we've got ice sheet mass. So ice sheet mass, I'm going to move me over. So ice sheet mass is pretty simply the mass of our Antarctic ice sheets. So as we go from 2003 again, no, earlier than that, 2002, sorry. As we go from 2002 to present, we see that we're losing 146 gigatons of ice per year. That is an extraordinary amount of ice to be losing. So we have lost in your lifetime about 2,000 gigatons of Arctic ice. That is a ridiculous amount of ice to be on. All right, so summer sea ice. So this is one of my favorite statistics because it deals with our polar bears. So summer sea ice is the smallest point of glacial and ice coverage. So we look at Antarctica at its very hottest time of year, its very hottest season, what part of that continent, what part of our North Pole is covered in ice during that extremely warm period of the year. And that has dropped by almost 13% every decade. So we've had about 13% less ice, which again, sounds like a small number, but when you think about it's a tenth of the entire northern pole of the globe of the world, that's an intense amount of area for us to be losing. And then that connects back to the amount of ice we're losing. And so when that ice goes away, it doesn't come back in the winter the way it used to. So evidence of climate change, we've got our ocean acidification. So this is the one that I think is particularly scary. And this is the one that I think is going to have the biggest and most immediate human impact because this involves our fisheries and whether or not we can actually get food from the ocean. So as atmospheric carbon dioxide levels increase, more carbon dioxide gets dissolved into the ocean. It's actually going to bond. So our CO2 and our H2O are going to bond, and it's going to become what's called carbonic acid, H2CO3. So those higher concentrations of that carbonic acid actually lead to a drop in ocean pH. So our ocean is literally becoming more acidic. So this is the amount of atmospheric CO2. This is the amount of carbon dioxide that's dissolved into the ocean. And this is the average pH of our ocean. So our pH is going down. Our ocean is becoming more acidic. And finally, it's our global average temperature.